Welcome back to a second example of surface integrals where the surface is a parameterized surface. So if our surface is given as the vector valued function r of u and v, we can rewrite the double integral of f integrated over the surface S with respect to S as a double integral over the region R in the UV plane by rewriting the function f as a function of u and v by replacing x with x of u and v, y with y of u and v, and z with z of u and v. And differential S is equal to the magnitude of this cross product differential A, where differential A would be du dv or dv du. And again, we did discuss where this extra integrating factor came from in the video on the area of a parameterized surface. Let's go and take a look at our second example. We're going to evaluate the given double integral where f is equal to x squared plus y squared and our surface is a unit sphere above the xy plane. So because our surface is a sphere, it'll be pretty easy to parameterize this surface using spherical coordinates. We'll just let phi equal u and theta equal v. So x is going to be equal to sine u cosine v. Y is going to be equal to sine u sine v. And z is going to be equal to cosine u. And u is going to be on the closed interval from 0 to pi over 2 since we're above the xy plane. And theta, or v, will be on the closed interval from 0 to 2 pi. Now let's start working on this integrating factor. So now we'll find the partial derivatives of r. So here we'll have cosine u cosine v cosine u sine v, and here we'll have negative sine u. And now for the partials with respect to v, we're going to have, this will be negative sine v, so we'll have negative sine u sine v. Here we'll have sine u cosine v, and here we'll have 0. Now we'll determine the cross product of these two vector valued functions. To do that, we'll evaluate the 3 by 3 determinant. We're going to go ahead and use the diagonal method, and I've already set that up to save some time. So again, here's the 3 by 3 determinant, but because I'm using the diagonal method, I copied column 1 and column 2 again. And now I'll sum the product of these blue diagonals, 1, 2, 3, and then I'll subtract the product of these 3 diagonals in green. And for the sake of time, I've already worked this out. It comes out to sine squared u cosine v, sine squared u sine v, and sine u cosine u. So you may want to pause the video and work this out. That's what it should come out to. And now we need to determine the magnitude of this cross product. I did show this part in another video. You end up having to factor the radicand twice. You end up with the square root of sine squared u, which is equal to sine u. So all of this gives us the magnitude of the cross product. Let's go back to the initial problem just for a moment. So all of this is equal to sine u, and now we have to rewrite our function f equals x squared plus y squared using x equals sine u cosine v and y equals sine u sine v. So let's go ahead and do that now. We're going to have sine squared u cosine squared v, there's our x squared, plus y squared is going to be sine squared u sine squared v. Again, remember our function f of x, y, z was equal to x squared plus y squared. So here's x squared, here's y squared. This magnitude here is equal to sine u, and then we'll use the order of du dv, where u is on the interval from 0 to pi over 2, and v is on the interval from 0 to 2 pi. Now we need to simplify this radicand. Let's see what we can do here. If we factor out sine squared u, we'll have cosine squared v plus sine squared v. That's going to be equal to 1. So we have sine squared u times sine u. That's going to be sine to the third u du dv. Let's go ahead and perform a trig substitution here. Let's go ahead and replace two of the factors, sine squared u, with 1 minus cosine squared u. And now let's go ahead and distribute the sine u. So we'll have sine u minus sine u cosine squared u. Now if we let w equal cosine u, dw is going to be equal to negative sine u du. Notice we have a negative sine u du here. So this second part simplifies to just w squared. Integrating this respects to u, we're going to have negative cosine u. Remember, this is going to be w to the second, so we'll have 1/3 w cubed, or plus 1/3 cosine cubed u. So when u is pi over 2, these will both be 0, and then we'll have minus, and then when u is 0, we're going to have negative 1 plus, this will be 1/3, so we have negative 2/3. Got the dv in here. So we have a positive 2/3. Let's go ahead and finish this on the next page. So we have 2/3 v. So we have 2/3 times 2 pi minus 0. That's going to give us 4 pi over 3. So this example was pretty involved. I did skip a little bit of work due to time, but I hope you found this example helpful.